Welcome friends to my YouTube channel. In my today's lecture I shall going to discuss a special type of collision that is called scattering. Okay, so what is this? Suppose there is a particle at rest. This is target and a particle with a velocity u, say, strikes the particle. Okay, and the target is at rest. Now after suffering collision, the incident particle scattered at a particular angle and the target particle recoils. Okay, so if this is the original line, so say scattering angle is theta 1 and recoiled angle is theta 2. Okay, and if after scattering the incident particle moves with a velocity v1 and after recoiling the target moves with a velocity v2. Okay, so this is the diagram. Okay, this is the diagram. Okay, say a incident particle moves with a velocity u and strikes a target that is at rest, and after collision the incident particle moves with a velocity v1 with a scattering angle theta 1 and the target recoils at an angle theta 2 with a velocity v2. Okay, so if we apply the law of conservation, we assume here we assume that incident and target are of same mass, that is same for simplicity. Okay, so what will be the law of conservation of linear momentum along x-axis? Say this is u1. Okay, so if we apply law of conservation of linear momentum along x-axis, so what will be the linear momentum along before collision? This. Okay, this equals to mv1 cos theta 1 plus mv2 cos theta 2. This is along x-axis. So u1, this is equals to v1 cos theta 1 plus say v2 cos theta 2. Okay, so this is the law of conservation of linear momentum along x-axis. So if we apply the law of conservation of linear momentum along y-axis, okay, so there is no particle because the particle initially moves from x-axis, so there is no component of y. So this is mv1 sin theta 1 and this is negative direction of x-axis, that means minus mv2 sin theta 2. So we can write v2 sin theta 2, this equals to v1 sin theta 1. Okay, these equations we get. Okay, so let us simplify this. So let us simplify these two equations and see what we get. Okay, so let us simplify these two equations. Now from this equation we can write v2 cos theta 2 is simply u1 minus v1 cos theta 1. Okay, from this equation we can write. Now if we take square, so v2 square cos square theta 2, this equals to u1 square plus v1 square cos square theta 1 minus 2 u1 v1 cos theta 1. We gave it a name 3, say. And from this equation, if we got take square, v2 square sin square theta 2, this is simply v1 square sin square theta 1. Okay, this gives equation 4. Okay, now if we add these two equations, then what we get? We get v2 square, this is simply u1 square plus v1 square minus 2u1 v1 cos theta 1. Simply if we add this, after squaring we will get two different equations, and then adding these two equations we will arrive at this equation. Now if you look back into the picture, if we apply energy conservation theorem, previously we are doing calculation on the basis of law of conservation of linear momentum. So if we apply energy conservation theorem, so what will be the initial energy? Half mu1 square. And what would be the kinetic energy? Half mv1 square plus half mv2 square. Okay, so we can write u1 square, this equals to v1 square plus v2 square. Okay, fine. Okay, so let us substitute that. If we substitute the value of u1 square here, that means v1 square plus v2 square. So what we get? So here we substitute v1 square plus v2 square plus v1 square means this minus 2u1 v1 cos theta 1. So v2 square cancels. So what we get? v1, this equals to u1 cos theta 1. Okay, this gives a name, say 6. So this is the scattering velocity. This is the velocity after scattering. Okay, v1 equals to u1 cos theta. Okay, u1 cos theta. Okay, now we get v1, this equals to u1 cos theta 1. Now if we substitute the value, say u1 square, this equals to v1 square plus v2 square. Okay, here if we substitute the value of this, that means u1 square cos square theta 1 plus v2 square. So what we get? We get v2 square, this equals to u1 square 1 minus cos square theta 1, that means u1 square sin square theta 1. So from which we get v2, this equals to u1 sin theta 1. Fine, we will get the velocity okay after scattering and velocity after recoil. Okay, v1 equals to u1 cos theta and v2 equal to u1 sin theta. Okay, okay, so we get v1, this is simply u1 cos theta 1, and v2, this is simply u1 sin theta 1. Okay, now this is the picture. Okay, this is theta 1, this is theta 2, v1, this is v2, this is u1. Okay, we previously found u1, this equals to mv1 cos theta 1, that is v1 cos theta 1 plus v2 cos theta 2. Okay, so here from which we can write v2 cos theta 2, this equals to u1 minus v1 cos theta 1. and also we find v2 sine theta 2, this equals to v1 sine theta 1. So what will be my tan theta 2? My tan theta 2 will be this divided by this, that means v1 sine theta 1 by u1 minus v1 cos theta 1. Okay. Okay. So if we substitute the value, that means of v1, that means u1 cos theta 1. So u1 sine theta 1 cos theta 1, and v1 is also u1 cos theta 1. That means u1 cos square theta 1. Okay. So if we simplify it, so we get tan theta 2, this u1 cancels. Okay. So sine theta 1 cos theta 1 by 1 minus cos square theta 1, that means sine square theta 1. So cos theta 1 by sine theta 1, this simply represents cot theta 1. Okay, that means tan 90 degree minus theta 1. So simply theta 2, this equals to 90 minus theta 1, or you can say theta 2 plus theta 1 equals to 90 degrees. So we have seen that after collision, the direction of scattering and the recoil, the angle between theta 1 and theta 2 is 90 degree. The scatter and the recoil objects are perpendicular to each other. This is our aim. Okay, we have to find out the velocity after collision of the scattered particle and that of the recoil particle, and the angle of scattering as well as the recoiled angle, the relation between them. Okay, so just to do it, these are the simple algebraic calculations. Okay, so this is the scattering process with respect to laboratory frame of reference. Okay, so this is up to today. So if you don't subscribe my channel, then kindly subscribe it to get latest videos. Okay, thank you.